Have you ever wondered when you're on the beach why on a hot summer's day the sand can get roasting hot, yet the water stays cold? Well, it's to do with specific heat capacity, and that's what today's lesson is about. If you think about it, it doesn't really make sense. The sun is shining in equal quantities on the water and the sand. Both, in fact, are absorbing the same amount of heat energy. Yet, bizarrely, whilst the water's temperature increases a little bit, the sand's temperature increases a lot. Putting the same amount of heat into some materials gives a bigger temperature rise than in other materials.
I have here two beakers. This beaker here contains 1 kilogram of water. This beaker here contains 1 kilogram of oil. I'm going to heat them in exactly the same way with the same flames for 5 minutes, and we're going to see what effect that has on the temperature. At the moment, the temperature of both liquids is the same as the room temperature, which is exactly 20 degrees. Just the flames, so they're the same, and I'm going to time them for 5 minutes. 5 minutes later, let's see what's happened. Now, the water has increased its temperature to 30. It's gone up by 10 degrees, whereas the oil has gone up by 20 degrees. Its temperature is now 40. They've both received the same amount of energy from the Bunsen burners, but this one's temperature has increased more. Why is that? The answer is to do with specific heat capacity. And specific heat capacity is a substance's ability to store energy. And actually water is very good at storing energy. It has a high specific heat capacity. Water can store twice as much energy per degree Celsius as oil.
So this is what I did. I had 1 kilogram of water in one pan and 1 kilogram of cooking oil in another, well, beakers actually, and I heated them for 5 minutes. After 5 minutes, the water had increased in temperature by 10 degrees to 30, and the cooking oil had increased by 20 degrees to 40. The water heats up less than the oil. The same amount of heat produces half the temperature rise in the water as the oil, yet they have both absorbed the same amount of energy. What could we do to make the same temperature rise in the water as in the oil? We could heat them for different amounts. So whereas before we heated the oil for 5 minutes and it went up by 20 degrees, to get the same temperature rise, we'd have to heat the water for twice as long. But of course then it would contain twice as much energy. This means water has twice the capacity to absorb and store heat energy as oil. You could say that more energy can be stored in 1 degree temperature-wise of water than it can in the oil. And actually this is true of lots of materials. Materials vary quite widely as to the amount of heat they can absorb for the same temperature rise. And there are no simple patterns or rules to this, although metals tend to have particularly low capacities. There are two ways of looking at this. At the top, we've got 4 materials: water, cooking oil, silica, which is rock, and copper. And if we put the same amount of heat in each, we see that we only get 1/4 of the temperature rise with water than with rock for the same amount of heat. Another way of looking at it is that we need to put in 4 times the amount of heat into water to get the same temperature rise as rock. So we say that water has a higher heat capacity than rock. Now, how do we measure heat capacity? Well, we need to measure how many joules of energy are put into the material, and how many joules of energy are needed to make each degree temperature rise. To be fair, there are other factors that we need to consider too, like the mass or the volume or the number of particles. In other words, all of these things kind of mean the amount. For GCSE, we use the term specific heat capacity, which compares the same amount of mass, 1 kilogram actually. And specific heat capacity is the amount of energy that is needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius. And of course there is an equation. Here it is. And I'm going to explain this equation to you in the laboratory next.
So this is the equation for specific heat capacity. Now the good news is you don't need to know this one off by heart. The bad news is it's got a bit of Greek in it. There's 2 Greek letters here, and these are letters that you're going to need to become familiar with. This triangle always means change in. Change in. So its name is delta, by the way. So delta E means change in energy. Change in energy. The other Greek letter we've got here is this thing that looks like an O with a line through it. This is called theta, and delta theta means change in temperature. C is specific heat capacity. So what have we got? The change in energy in the water or the oil is equal to the mass of the water or the oil multiplied by its specific heat capacity multiplied by the change in temperature. So we can rearrange that equation if we want to work out the specific heat capacity, and the specific heat capacity is this. C, specific heat capacity, is delta E, change in energy, divided by the mass times the change in temperature. And we're going to use this equation now to calculate the specific heat capacity of aluminium. Okay, so what we're going to try and do now is to calculate the specific heat capacity of aluminium. Here's a block of aluminium, and this block very conveniently has a mass of exactly 1 kilogram. This is what's called an immersion heater. When I turn it on, it's going to get hot, and it's going to heat the aluminium from within. That slots into that hole there, and there's a narrower hole next to it where a thermometer can go in, and that will tell us the temperature of the aluminium as we heat it up. The other bits of equipment I've got here are a voltmeter and an ammeter and a power pack. And I'm going to do a calculation with the voltage, the current, and the time that it takes to heat, which will give me an indication of how much energy I'm putting into the block. So all I'm going to do is switch the thing on and time how long it takes for this block to increase in temperature by 5 degrees. It's 20 degrees at the moment. I'm going to keep on heating it until it gets to 25 degrees. The voltage, the potential difference, is 4.25 volts, and I've got a current of 1.4 amps at the moment. So we'll just keep on heating that until it increases by 5 degrees. Okay, so it increased by 5 degrees. It took around about 12 minutes, and I've done a little bit of maths here to work a few things out, which I won't trouble you with now. But what I've calculated is that in that 12-minute period of time, 4,234 joules, that's that number there, 4,234 joules of heat, internal energy, were put into that aluminium block. So we can use this equation now to work out the specific heat capacity of aluminium. Here we go, let's give it a go. So 4,234 divided by the mass the mass was 1 kilogram. That's nice. And delta theta is the change in temperature. It went from 20 to 25 degrees, which was an increase of 5 degrees. So it's the change in temperature, not the end temperature. So it's that number divided by 5, which I can't do in my head. Let's give it a go. Here we go. 4, 2, 3, 4 divided by 5 is, oh, that's not right. 4, 2, 3, 4 divided by 5 is 847. 847. Oh, 7 joules. That's a 7 there. And that's the answer that I calculated. Now, actually, the specific heat capacity of aluminium is 900 joules. So that's not quite right. I wonder if you can think of any reasons why we're not getting a 100% accurate answer on that experiment.
Here's a diagram of the apparatus that you just saw. Now this experiment is actually one of the required practical activities for GCSE combined triple science. But we're not going to even attempt to get you through that whilst you're at home. We'll do that when you get into school in September, hopefully, so don't worry about that too much now. For now it's enough just to know that this exists. Instead, let's have a look at a couple of questions that could come up, the sort of style of questions. The first question here involves just using the equation. The second one involves rearranging the equation. So let's have a look at the first one first of all. A beaker filled with 0.1 kilograms of water with a specific heat capacity 4,200 joules per kilogram degree Celsius. Look at that clumsy unit there, but that's the unit of specific heat capacity. It's heated from 20 degrees Celsius to 80 degrees Celsius. So what's the temperature change then? What would delta theta be? Hopefully you just said 60, because that's the answer. Calculate the amount of heat energy gained by the water. I shall give you 30 seconds to have a go at that, and then I shall reveal the answer. Get your calculators out now, please, and have a go. Here it is. The mass is 0.1. Multiply that by the specific heat capacity of 4,200 and multiply that by delta theta, the temperature change, which is 60, and you get 25,200 joules, which can also be written as 25.2 kilojoules. Well done if you got that right. Here comes the next one. Another beaker containing 24 grams of water starts at 50 degrees Celsius. If it loses 2,000 joules of energy, what temperature has it dropped to? Now the first thing to do here is to rearrange the equation so that you get delta theta as the subject, the temperature change. And when you've got that, then all you need to do is subtract that from 50, and that should give you the answer. 30 seconds starts now. So there's the rearranged equation. Delta theta equals delta E divided by MC, which is equal to 2,000, that's delta E, divide that by 0.024 times 4,200. Careful of the brackets, and that should give you a temperature change of 19.8 degrees Celsius. So it started at 50. It's fallen by 19.8 degrees, so what's it fallen to? That's what the question is asking, and the answer is 50. Take away 19.8 and you get the answer of 30.2 degrees Celsius. Here's another style of question, a longer answer style of question. If you eat a pizza from a hot oven, the crust might be harmless, while the cheese topping scalds your tongue. Use your ideas about specific heat capacity to explain why. Give you just 10 seconds or so to think about that. And it's an answer a bit like this. The crust has a lower specific heat capacity, so the cheese stores more energy and therefore holds the heat in for a longer amount of time. The key point is the first point there. The crust has a lower specific heat capacity. Here's another one involving a calculation. Using this equation, which you don't need to know, but you will be given in an exam, how much energy would be transferred to raise the temperature of 2 kilograms of water from 20 to 30 degrees Celsius? And here they're giving the specific heat capacity of water, slightly different number, 4181. What have we got to do here? Well, this is straightforward, isn't it? We don't even need to pause and think about this. The energy change, if we look at the equation, the mass m, that's 2, multiply that by the specific heat capacity, 4181, multiply that by the temperature change, which is 10, and you should end up with an answer that looks like this: 38,620 joules. Could you write that as kilojoules? Hopefully 83.62 kilojoules is what you would have said. One more. The specific heat capacity of water is 4,181 joules per kilogram degree Celsius, and that of lead is 128 joules per kilogram degree Celsius. If you had both the same mass of lead and water, which one would require the most energy to heat and why? Which one would require the most the most energy to heat? Lead or water? Hopefully you said water, because it has a higher specific heat capacity. In other words, it takes more energy to raise it by 1 degree. This question has come up in different forms in exams over the years. Radiators can be either filled with water or filled with oil. Water has a higher specific heat capacity. What are the advantages and disadvantages of each? Well, water will take longer to warm up. So if you're cold and you turn the radiator on, the oil heater will warm you up sooner. But the water will store more energy, and so when you do turn it off, it will stay warm for longer. That could be considered an advantage. It's still giving out heat for a longer time after the oil-fired one has stopped working. There we are. That's pretty much it for this lesson. There's one extra bit that's going to follow on now for the triple science students. This is the end of the film for the combined science students. The next task for you to do is an educate task. Good luck.